In this review of Chapter 5, I want to do some basic nomenclature problems. I just pulled some from the textbook here. And along the way, I'll illustrate a few other subject matters like acid nomenclature as well. So this first question is dealing with, well, a couple things. I mean, identification of the particular polyatomic ion. So phosphate here has a PO4 with a -3 charge, and it wants me to figure out what the formula is for phosphate when calcium binds with it. Now, calcium is one of our ions that maintains a constant charge, right? It's always a +2 state. And then just a reminder, right, that's coming from these periodic trends in the ionic charge formation. And you can see that all the alkaline earth metals form a +2 charge. So since it's one of those that since it's one of those that only has a single charge on it, single positive charge, then you do not need a Roman numeral, right? A Roman numeral is only needed for those transition and post-transition metals that have more than one charge associated with the cation, and we'll talk about those in a minute. So notice what we have here. We do not have equal and opposite charges, so they can't come together in a 1-to-1 ratio. Instead, what we're going to do is we're going to use that little flip-flop rule to figure out how many of each. So the 3 here tells me I need 3 calciums. The 2 here tells me I need 2 phosphates. And when you're trying to show multiple polyatomic ions, you'll always want to put parentheses around the polyatomic. Right, so that 2 is now translated for all of those atoms in that polyatomic ion. And let me just take a moment and then use this to also discuss hydrogen phosphate. So hydrogen phosphate, well, one way to look at this is that what you're doing is you're bringing a hydrogen cation together with the phosphate anion, and you get something new. Right? Positive charge on the hydrogen. This is essentially a proton. This is a hydrogen nucleus, but it has a H+ formula. And you know, if we do the math here, 1 minus 3 gives me a -2, so that changes the charge overall on this ion. And you can imagine now, like, this can act as a polyatomic associated with something like calcium. And so, for example, since now +2, -2, they are equal and opposite, then they would just come together in a 1-to-1 ratio. I can continue with this trend of adding protons to these this anion here, and if I add 2 more, what's going to happen now is that the +2 and the -2, those charges are going to cancel themselves out. Very much similar to what happens in a salt formula. Now, this is not a salt. This, as it turns out, is a molecular compound, and we'll talk more about these later. But what I want you to notice is that we don't use like this hydrogen name now in the name. This is actually called phosphoric acid. Now, we didn't do any kind of elaborate set of nomenclature rules for the acids. Basically, what you just need to know is a set of common acids or important acids. And there's phosphate or phosphoric acid right there. And something in the video I did talk about how, you know, you can add protons here to form these different acids, and then there's this change in the ending on the name. You know, a phosphate goes to phosphoric acid. Now, in this problem here, we want to go from the molecular formula to the name. Now, there's a few here, like the magnesium, potassium, barium. They are actually, there's what I said magnesium, potassium, barium. These are some of those well-behaved ions that only form a single charge. And so all of those salts, I do not need a Roman numeral. The other ones there, one was iron, one was copper, and one was lead. Notice these are all those transition, post-transition metals that can vary in charge, we'll need a Roman numeral for those. Let's do one of those, one of these first though. Let's just do this bottom one here. So this is magnesium acetate. I don't need a Roman numeral because, again, magnesium is always a +2 charge. And then the other thing you need to appreciate is that, especially when you see those parentheses, that is a polyatomic sitting in there. So you're not going to name these polyatomics like dicarbon trihydrogen dioxide, something like that. You don't do that. When you see this symbolism, that is acetate. Now the other ones here, let's do C and D real quick. Pretty much whenever you get those transition metals or post-transition metals, you're doing something like this. It's a question mark about what the charge is going to be there. Now the one thing you'll always know is actually the charge on the anion. What you're going to do is you're going to use this information to figure out what the charge is for the cation. Now notice I had 2 of the nitrites. What's the total charge here now? It's a -2 here. Well, when one of these and 2 of these come together, we form a salt that has no charge. The charges have been canceled out. And so that means that this must be a +2 state. +2 state, now we're going to use that as a Roman numeral. Copper 2 nitrite. So nitrite has the 2 oxygens, nitrate looks like that. And the other one with lead, same thing, right? That's a question mark. You got to know your sulfate, -2 charge. Now, in this formula, they're coming together in a 1-to-1 ratio. For every lead cation, there's 1 sulfate anion. That means the charges have to be equal and opposite. So this one is also a +2. And just like before, we're going to use our Roman numeral 2. So lead 2 sulfate. So here's an example where we're going the other direction. We're given the name. We want to figure out what the molecular formula is. Now with the transition metals, when you're given the name, I don't know, in some ways it might be easier if you can remember that Roman numeral is a charge. Right? 1 means a +1 on the copper. Chlorate has this molecular formula and it has a -1 charge. So notice, equal, opposite, they're just going to come together in a 1-to-1 ratio. So CuClO3. And it's done. Now we'll comment a little bit here. If you were given this particular formula and asked to name the compound, again, right, you need to realize, okay, the Cl and the O3 are actually stuck together to represent chlorate. It's not the kind of thing where copper 2 chloride trioxide. That's not correct. And the next one, calcium fluoride. Now I didn't hesitate putting that +2 charge there, even though there's no Roman numeral. Again, what we have to realize is that calcium, right there, right, it's one of those well-behaved cations, the one that can only form one particular charge. In this case, a +2. Right, this is just a periodic trend. +1, +2. There's a +3, right, for those guys. And then once you cross over the carbon column, and then it starts counting down. -3, -2, and maybe actually that looks a little better. So it's not a 1-to-1 ratio. So what we're going to do, the 2 there tells me how many of these that I need, and then the 1 there tells me how many calciums. That's it. Notice that I'm not putting parentheses around these monoatomic atoms or ions. The parentheses are only needed for multiple polyatomic ions, like you saw in this problem. And the last topic was dealing with these molecular compounds. So one thing to note about molecular compounds, all nonmetal elements. And basically, where we're at here, this divider, these are our nonmetals. And you can include the ones that are touching the line here as well, these metalloids in this group here. And these are our metals. Right? Metals plus nonmetals, those producing those ionic compounds. All nonmetals, including the inert gases, they are going to make them these molecular compounds. Sometimes you hear the phrase binary molecular compound, binary, just 2 things. Okay, and those are the only ones that we're going to be naming. Let's see, let's do this one and that one. One reason why I want to do this one is just to compare it for a minute. So let's actually name SO3. So SO3, no charge on it. First element is sulfur. And then we have 3 oxygens, trioxide. All right, we need to know our Roman numerals. Mono, di, tri, tetra is probably going to be the most common one. You will see a penta. We'll use penta in just a second. Remember the rules here, and you'll want to go back and look at the video in chapter 5 for molecular compounds. If there's just a single element on the first, then the mono is left off. So no mono there. And then other than that, tri, so tri indicates the 3 there. Now, I said I wanted to compare it with something else. I wanted to compare it with SO3 with a -2. That's a different compound. Okay, this is a sulfite ion. Those are involved in like polyatomic. Well, it is a polyatomic atom involved in ionic compound formation. And then the other one I want to do is this guy here. So one reason I picked it, actually a couple reasons. I have something other than just 1 on the first atom, okay? For 2, that's di. So we do include di or tri, whatever is on the first atom. It's only the mono that we skip. So diiodine, okay? We keep the double I's, okay? Whereas, remember our rule for oxide, this is not going to be pentaoxide, it's actually going to be pentoxide. So that A is removed like this. It's not tetraoxide, it's tetroxide. It's not monooxide, it's monoxide. So again, check back at that video for naming molecular compounds to see the full set of rules there, even though that what I listed here includes the full set of rules. And then going in the opposite direction where you're given the name, going to the formula. I mean, in some ways, this one may be easier because the numerical values are just explicitly given, okay? Unless mono, like xenon hexafluoride. So since there's no, right, mono is left out for the first element, so there's just 1 xenon, and then hexa, that's 6 fluoride, that's F. Down here, tetra phosphorus, tetra's 4, and then triselenide, well, that is the ide name for selenium. Let's just take a quick peek. Selenium is right there. So that tri, that's 3. That's it. Thanks.